Good morning, everyone. Myself, Ashish Verma, and this is our end semester exam solution part 1. So let's begin with question 1. Discuss between hypothesis driven and data driven paradigms of in data science. Provide an example of each. Hypothesis driven analysis follows the traditional scientific approach where the analyst starts with a predefined hypothesis and then collects and tests data to confirm or reject it. The process is guided by theory or prior expectations. Example, a policing analyst hypothesis that cases with no witness take longer to resolve and test this using complete resolution data. And what are data-driven analyses are something that does not begin with a fixed hypothesis. Instead, patterns and insights emerge directly from the data using exploratory analysis or machine learning methods. It allows unexpected structure, correlations, or clusters to surface without prior assumptions. Example, using clustering on large complaint logs to discover previously unknown groupings of offenses or emerging hotspots without any prior theory. For example, hypothesis driven starts with a predefined assumption and tests it using data, while analysis lets pattern emerge directly from the data without prior confirmation expectations. Uh, for example, it's testing whether cases without witness takes longer to resolve. A data-driven example is using clustering to discover known offense patterns. Now, difference between structured, unstructured, quantitative, and categorical data with suitable real-world examples. First, structured data. Structured data refers to information that is organized into fixed fields, rows, and columns, making it easy to store, search, and analyze using database. It has a well-defined schema and strict formatting rules. Real-world example: police complaint register stored in SQL tables containing attributes like FIR number, date of incident, accused age, offense section, and police station ID. Unstructured data does not follow a predefined data model and is often free-form, irregular, or multimedia in nature. It requires specialized processing techniques such as NLP or computer vision. A real-world example: narrative text of complaints, body-worn camera footage, scanned written statements, audio recordings of distress calls, or social media screenshot attached to cases. Quantitative data includes numerical values that represents measurable quantities. Such data supports arithmetic operations and statistical computations. It may be continuous or discrete. Real-world example: incident duration in minutes, estimated financial loss, number of accused persons, evidence strength scores, or count of exhibits seized. Categorical data represents labels, groups, or qualitative classes rather than numeric measures. It cannot be meaningfully used for arithmetic operations but is useful for classification and grouping. Real world example: offense category, theft, assault, jurisdiction name, gender of complaint, presence absence of witness, or severity level. Now, question 2. Write an algorithm that utilizes Bayes' theorem for decision making. Naive Bayes is a probabilistic classification algorithm that applies Bayes' theorem with the assumption that features are conditionally independent given the classes. It is used for decision making by choosing the class with the highest posterior probability. Algorithm: Naive decision making. Input a set of classes C1, C2 up to Ck. Training data for estimating priors featuring childhoods, likelihoods. A new case x is equals to x1, x2 up to xn. Steps: compute prior probability for each class Ci from training data. Compute likelihood for feature xj under each class Ci. Apply Bayes theorem. Compute the posterior score for each class. Choose the class with the highest posterior score. Output the predictor class and its probability, which is argument max Ci of p. Now question second of B. Write any suitable algorithm for association rule mining that can print all association rules. Algorithm a priori for association rules mining input. Transaction database D. Minimum support, minimum confidence. Output all association rules that satisfy min sub and min conf. Steps for it are as given as follows. Scan the database to find support of each item. Keep items whose support generate candidate K item sets. Scan the database and count support for each candidate in CK. Keep only those candidates whose support means up. This becomes LK. D. Stop when no frequent item sets are found. Step 2. Generate association rules from frequent item sets. For every non-empty subset A of F, let B is equals to F minus A. Compute confidence is equals to support F divided by support A. If confidence means output rule AB with its support F and confidence. This procedure prints all association rules that meet both thresholds. Compute mean, median, mode, and standard deviation for given small dataset. Explain when each measure is appropriate. Consider the marks of 8 students in an internal exam test. Marks are 42, 55, 55, 60, 63, 70, 75, 90. So the mean is sum of all marks divided by the number of students. Sum of all marks is equal to 510 and number of students are 8. So the mean is 63.75. The mean tells us the overall average performance of the class. It is useful when the marks are fairly balanced, but it can be pulled upward or downward by extreme scores like the 90 here. Median or middle value. Since there are 8 values, median is equal to average of the fourth and fifth values in sorted order. Sorted order is 42, 55, 56, 60, 62, 75. In median, 60 divided by 60 plus 63 divided by 2 gives us 61.5. Explanation. The median represents the typical student performance. It is not affected by the outliers. Even if one student scores extremely high or low, the median remains stable. Now the now the mode, the most frequent value, the value that occurs most often, that is 55. The mode shows the common score in the class. This is useful when identifying common performance levels or popular score ranges. Now standard deviation. As you can see, standard deviation measures how much the values in the dataset deviate from the mean. It quantifies the spread or variability of the data. So the sum of squared deviation is equal to 149.5 and it's divided root of 1495.5 divided by 7, that is equals to 15.48. So the standard deviation when comparing variability of mark or identifying how consistent the class is. What is the difference between errors and artifacts of in data cleaning? Explain into imputations. Errors in data cleaning refer to incorrect or false values that arise from mistakes in entry, recording, or measurement. Examples including wrong dates, impossible ages, or mistyped numbers. These values do not reflect the true real world information. Artifacts, on the other hand, are distortions or anomalies introduced by the data collection or processing system itself. They are not wrong in the sense of human error, but are byproducts of sensors, OCR tools, extraction pipelines, or formatting rules. For example, repeated tokens from text extraction, duplicated entries created by syncing systems, or missing fields caused by template changes. Two imputation techniques: mean median imputation. Missing numerical values are replaced with the mean or median of the existing data. Mean is suitable for roughly symmetric data, whereas median is preferred when the data has outliers. It is simple and preserves dataset size, but reduces variability. Class-specific imputation. Missing values are filled using statistics computed within each class or category. For example, missing marks for students in a particular section can be replaced using that section's mean rather than the overall mean. This improves accuracy when different groups have different distributions. Now question number fourth of A. Explain the four common features engineering techniques for continuous or categorical data. Normalization. Continuous features such as age, income, or severity scores are rescaled using methods like mean, maximum, scaling, or z-score standardization. This prevents large valued attributes from dominating models and improves convergence in distance-based methods. Binding discretization. Continuous variables are converted into categorical intervals. For example, complaint severity scores may be grouped into low, medium, and high. Binding reduces noise, handles outliers more robustly, and allows algorithms that works better than categories. One hot encoding for categorical data. Categorical attributes such as jurisdiction or offense type are converted into binary indicator variables. Each category becomes a separate column with values 0 or 1, enabling algorithms to work with non-numerical labels without imposing an artificial numeric order. Feature extraction and transformation. Complex or high-dimensional data is transformed into more informative features. For text complaints, TF, IDF converts narrative text into weight term vectors. For numeric data, PCA reduces dimensions by creating a new uncorrelated features that capture maximum variance. What is sampling from a distribution? Describe inverse transform sampling or Monte Carlo sampling. Inverse transform sampling. Inverse transform sampling generates samples from any continuous distribution using its cumulative distribution function. Draw a random number u from uniform 0 to 1. Compute x. The value of x is sampled from the distribution. Example. To sample from an exponential distribution with rate lambda is equal to 1. The Monte Carlo sampling. Monte Carlo sampling repeatedly draws random samples from known distribution to estimate quantities of simulate outcomes. Example, to estimate the value of pi, randomly generate points in a square and count how many fall inside a circle of radius 1. The ratio of points inside the circle to total points approximates pi by 4, repeating many random samples, improving accuracy. Thank you.